All right, welcome to the end of physics, or almost. We have today's lesson and one lesson next week, and then we'll be done. We're getting close to the end of the year, albeit it's a little shorter than usual and a little shorter than we would all want, I think. Um, but welcome to the end of physics, or have we really just begun? All right, let's do a little bit of review. Since we're at the end of physics, let's do a little bit of review of what we have done this year. Okay, what have we learned? We've talked about kinematics, one-dimensional, two-dimensional kinematics. Two-dimensional kinematics we called projectile motion before, but I just combined it into one here because it's the same idea. All right, for that we had four kinematic equations. Forces, right? Net force equals mass times acceleration. We talked about momentum, mass times velocity, right? We talked about work and energy, if these two things go together. But this is the four central topics of physics that we have studied. There's a lot more we could have. The one thing that I'm really sorry we would not be able to cover would be like current electricity. We set up batteries and light bulbs and figure out how that works. But what does that involve? That involves energy, right? I mean, do you need energy to make a fan work? You need energy to see me talking to you on the screen, right? It talks about forces, right? Potential energy, and forces. So you have to push those electrons through the wire. So it's anything else that we might talk about: current electricity, electrostatics, the force between charged particles. Fluid dynamics, we're talking about particles moving through a fluid, that would be liquids or gases, right? Talk about nuclear physics. All these things are all just one or more of these four topics. The language will change, but it just involves those four topics, and that's it. Okay. In addition to that, what we have really done so far is to talk about, even when we had, I would draw a car and the car is moving down the street. We considered the car to be a point particle. We considered it to have no physical extent. We just drew a pretty picture, in my case, an ugly picture. But in reality, something has a physical extent. Let's say this is a door and this is a hinge, so the thing can rotate in one direction or the other. Okay, and we apply a force on the door right here versus right here versus right here, depending on the force that we apply. Or the position at which we apply the force, we're going to get a very different motion of that door, right? I mean, if we push down here, the door is not going to rotate at all. We push over here, the door is going to slam shut, okay, for the same force. All right, so we have this whole nother world, a parallel universe, if you will, of problems that involve rotational characteristics. Okay, so all these four topics, we could talk about rotational kinematics, the study of how quickly something speeds up or spins up or spins down. So we can talk about angular acceleration, angular velocity, like RPM, right? The old time records, you'd have 33 1/3 RPMs, right? We could talk about angular forces. Angular forces are called torques, right? You've probably heard of torques. We could talk about angular momentum, right? You've seen ice skaters. They bring their hands in, they spin faster. They put their hands out, they spin more slowly. Okay. We could talk about rotational energy, right? I mean, kinetic energy is the energy due to motion. You can move in a straight line or you can spin, right? So you have this whole parallel universe of topics that we can study. And it's done in exactly the same way. These four topics, we just have those same four topics, but we talk about things that are rotating. Okay, so it's something that is very simple to do. You've already seen it. If you go into, if I'm lucky enough to have you in APC, we get to do that all over again for rotational motion. All right, so that is what we have done. I may have to pause from time to time to get this thing to work, but there we go. This is how we've learned physics. We've studied this. We started the year talking about kinematics. Then when we talked about kinematics, we talked about forces, then we talked about momentum, and then we talked about energy. All right, this is the logical sequence of how things are usually taught. Although there are some teachers that do it backwards. I tried that once. It was a disaster. I'll never do it again. And I laugh at all the teachers that try that. That's how we learn physics. we do physics in reverse. All right, we do physics starting from energy and momentum considerations. That's what we're going to be talking about today. We're going to be talking about conservation. That's what I mean about doing physics backwards. We start from conservation of momentum. We start from conservation of energy when we analyze a physical situation. Ultimately, let me just philosophize for a second, if you will. Ultimately, physics is about forces, right? We want to understand the forces between particles, and those particles can be subatomic particles, so we're talking about the teeny tiny, the quantum world, or it can be astrophysical, so we're talking about galaxies or a group of galaxies colliding. And we're trying to understand that interaction. Now, you guys think you know this stuff, right? Gravity, G m1 m2 over r squared, all that fun stuff. But it's obviously much more involved than that. If you just open up the newspaper and every other week there's articles about dark energy and dark matter. What is dark energy and dark matter? We don't know. That's why it's called dark. To shine a light, pardon the pun, on what that force is, we look at principles of conservation of momentum and conservation of energy, because they should be conserved in these dark matter and dark energy situations. Okay. So we do physics starting from momentum and energy, so that we can understand in a more fundamental way what the forces are that govern this universe. Okay, so enough about philosophizing. Let's move on to conservation laws. Okay, you've seen conservation laws. Conservation laws under certain circumstances, right? Under certain circumstances that we have already learned. All right, using the physics that we've already learned. Under certain circumstances, we are able to simplify our analysis of the phenomenon of the study. Okay. If we're able to do that, it requires a lot less work, pardon the pun, on our part to get to work through that problem, and also gives us more in-depth understanding of how the universe works on a more fundamental scale. Okay. So, for example, again, this is a little bit of a review. Mrs. Starita covered this a couple weeks ago. We have the impulse momentum theorem that you see on the screen. The net force, that is the net force, all the forces that are acting. This is a vector, remember? So we have x direction, y direction, z direction separately. The net force times the change during time times the time interval during which that net force is acting is going to equal to the change in momentum of the object that force is acting on. Okay. Ultimately, that is the basis of conservation of momentum. Conservation of momentum would be that this is zero. Under what conditions is that zero? That's equal to zero when the net external force is equal to zero. Okay, that allows us, and just as a quick recap, suppose you have two objects that are moving towards each other, they collide, stick together, bounce, whatever, I don't care, right? If we chose this as our system, right, then the only forces acting are internal. We have this force and that force. Those are action-reaction pairs. Those are the velocities. But these two guys collide. I push on you, you push on me. That's an internal force that would cancel. And so here the momentum would be conserved. If, however, we make the same diagram, but we call this our system instead, then momentum is not conserved, because these guys are going to collide, but that the force that this guy exerts on this guy, which is in that direction, obviously, that force is cutting through the boundary of our system, and momentum would not be conserved. This was the whole idea between for those some of the questions that you had on the labs with the blow dart and the kids sitting on the cart that they pushed off each other. You were asked questions about the individual cart as opposed to the combined carts, right? So you at one point you were focusing on momentum not being conserved, and another part you were focusing on momentum being the total momentum being conserved, looking at both of them together. Okay, so there's a question of what is your definition of the system. Okay, I may have to pause this video from time to time to get this program to work correctly. This seems, oh, there we go. All right, let's talk about some pillars of physics. I mean, one of the pillars of physics is momentum, conservation of momentum. When there's no net external force, then when there's no net external force acting on the system, and it's up to you to define the system. When there's no net force acting on the system, then momentum is conserved, in which case it makes our life a lot easier. Okay. There's another one involved, and that's total energy. Total energy is always, 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 always conserved. Okay. That's the total energy. If you consider it's all the energy from all the sources, right? The total energy is always conserved. You've seen this before. You've done this in chemistry. You did this in middle school. You jump on the potential energy is equal to kinetic energy at the bottom. All right. So we've done this before. But there's other sources of there's other energy conservation laws, which that does not include the word total. And we'll look at that. Okay. But let's start from scratch a little bit. This what you see here is a little bit reminiscent of what we did in the beginning of the year when it first started. I drew a kinematic diagram, right? Oops, I went backwards there. I didn't want to do that. I drew a kinematic diagram where we had. Come on, stop that. Right, I drew, say, a car. Some initial position of a car and a final position of the car. The car was moving with some initial velocity, it had some final velocity. We had the displacement, we had the time, and we had the acceleration. Right, the acceleration was a vector also. This looks very much like what's going on here. We have a displacement, we have kinetic energy rather than velocities, so it's like 1/2 mv squared instead, but it's the same idea. Okay, this is just a schematic. It's not used to solve anything. It's just to set up the ideas that are going to be coming. Okay, so we have this initial state. You're sitting on a bicycle, right? You go from this initial state to some final state. You have some initial kinetic energy, meaning you have some initial velocity in some direction. You have some final kinetic energy in some final direction, not necessarily the same as here. Right? Why would it change? Because there's a net force acting, right? And you start here and you end here, so we have a displacement. So we have forces acting. Those forces can change or whatever, but let's just take the net force here to be constant. Okay, and so we have FD cosine theta. Right? We've already seen all this stuff, right? So if we look at that. The energy here. Now, I'm not talking about when we talk about the initial state kinetic energy. I talk about the total energy. I'm not referencing here potential energy. We'll talk about potential energy next lecture, okay? Even though you know what it is, we're not going to consider it part of this yet because it's going to involve the forces that are acting, all right? And when we talk about gravitational potential energy, it's always with respect to some force that's acting, and we'll get to that next time. So right now, the only energy we're really considering is... All right, I think I got to pause, perhaps. No, there we go. So the total energy is conserved. So the total energy you start with, right? The total energy we start with is going to be the total energy after, plus the energy that we put in, plus the work that we put in. Okay, so the total work done. If you take the total work done, that work can be positive or negative. Right? So we could be putting energy in. Remember what work is. We can be creating energy, or we could be taking energy away. As far as work is concerned, we could be putting energy in, taking energy out. But the total energy before plus the work done that you do must be equal to the total energy afterwards. Okay, so it's a very, very simple concept. What's the initial energy? Is just simply the initial kinetic energy, 1/2 mv squared, right? The net work, this is the net force, so we're talking about the net work. So it's FD cosine theta, and again, I'm simplifying this, so we're talking about the constant force and a constant angle and a constant motion there. That's going to be equal to 1/2 mv final squared, okay? And here's the initial kinetic energy, final kinetic energy. We bring them together, right? Bring the initial kinetic energy over to this side. We get the change in kinetic energy is equal to the net work done. Really, really very simple. That ultimately is the conservation of total energy. It's not called the conservation of total energy. It's called the work energy theorem, which I wrote on the next slide. But I have derive this, if you will, using conservation of total energy that you already know. In reality, it's done the other way, right? In reality, this will come from our concepts of physics that we already have. It takes some calculus to do that. I'm not going to bother, but this is more. This is the fundamental idea. All right, we start with this. All right, this comes from just forces, right? With knowledge of forces, and again, if we brought in calculus, it's not that big. It's not that big of a deal if you know calculus to show this. But the net work done by all the forces is going to simply be equal to the change in kinetic energy. Okay. But right now we're just calling it the work energy theorem. The conservation of total energy is actually just a reformulation of the work energy theorem. Okay, and then there's conservation of mechanical energy, and we'll get into those distinctions in the next class. Okay, let's try to get this thing going here. Oops, okay, it's down there. Just as a little reminder, the network, W net is the network due to all the forces, okay? All right, so here's the work energy theorem. Okay, the network is the change in the final kinetic energy minus the, it's equal to the final kinetic energy minus the initial kinetic energy. So this is relatively straightforward to use, right? You either know the final velocity or you know the initial velocity, right? If it starts from rest and you end at rest, then the change in kinetic energy is 0. If you're moving at constant speed, the change in kinetic energy is 0. The Earth going around the sun, assuming that the Earth is moving at constant speed, the change in kinetic energy is 0. Okay, and this would be the net work done by all the forces. So guess what we need to do? We need to identify the forces that are acting. We need to draw a free body diagram. All those things that we have been that I've given to you throughout the year, drawing a free body diagram. All these things are still in play. How do we deal with this? For example, all right, these are very, very simple problems. Work energy theorem. Suppose you have a climber, a 95 kilogram climber climbing a 1,500 meter tall mountain. Okay, I got this pretty picture of people climbing a hill as opposed to a mountain. But you know, how you find the work done by a climber climbing a mountain? I have no idea. All right, what's work? What's work, you ask? Well, work is what? F d cosine theta. Now, as this climber is climbing, you know, we're trying to find the work done by him. So what we really have to do is calculate the work done, the forces acting on him as opposed to the forces that he's applying on other things. Right? What is he applying forces to? He's pushing on the rock, so the rock pushes back. So we have these action-reaction pairs that we'll deal with. But you know, he's applying a force, but the thing he's applying a force to is not moving. Well, in reality, it is, right? I hurled myself against a wall. Well, actually, I didn't. I did. We got put out of school before I did that. But if I hurled myself against a wall, I will move the earth, right? You drop your keys, you move the earth. So we could calculate that. And that would actually be kind of easy to calculate. But the work that this climber is doing is changing constantly. The forces that he's applying are the magnitude's changing, the direction is changing. Just look at the shape. Where's my pen? Just look at the shape of this thing. The contour is changing constantly. There's no way that you're going to be able to calculate that. So it seems like it's an impossible situation. But it's not. Okay, nothing is impossible if you know physics. All right. So how can we do this? Well, we used a work energy theorem. First of all, we need a free body diagram. We have to identify all the forces that are acting. We have gravity acting, mg. We have the normal force, right? The normal force is the force that the mountain is exerting on the climber, right, to keep him from going through the mountain, so perpendicular to the surface at that point. And the force exerted on the climber, that would be actually a friction force. So he's pushing against the ground pushes him forward. So that's really friction force, okay? So how are we going to do this? We have to use the work energy theorem, right? The work energy theorem, remember, is the net work done by all the forces that are acting. Now look at these three forces. Gravity is easy. The normal force, do you remember what the work done by the normal force is? Pause, 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 pause. It's a really simple number. We'll get to that in a second if you don't remember. And then the work done by the climber, which I just indicated was really difficult to figure out. Okay, so let's use the work energy theorem. So you come to a mountain. You want to climb this 1,500 meter tall mountain. You sit there and you go, crap, I don't want to climb that thing. So you stare. First of all, you're not moving. So the initial kinetic energy is zero. You're just looking at this thing going, why am I wanting to do this? And then you get to the top, you're exhausted. So you stop and you want to take a pretty picture. So your initial kinetic energy is zero. Your final kinetic energy is zero. Okay. So we're going to use the net work equals to the change in kinetic energy. The change in kinetic energy is zero, just like I said. Okay. Here's the answer to my question from a minute ago. The work done by the normal force is always zero. Okay, so this guy is zero, right? What's the work done by gravity? The work done by gravity is simply minus mgh. Gravity is down, the guy's moving up. Gravity does negative work, so it's minus mgh. Hint, that's the potential energy, right? But again, we're pretending we don't know what kinetic energy is yet, but you know what it is. So it's the work done by the normal force is zero. The work done by gravity is, stop that. The work done by gravity is minus mgh, and the work done by the climber is what we're looking for, okay? And that sum must be equal to zero because the kinetic energy was zero to start with, the kinetic energy is zero afterwards. What we want to do is find the work done by the climber, put the numbers in that we know, 95 kilograms, G is 10, 9.8, and the height is 1,500 meters. You put that all together, you got 1,425,000 joules done by the climber to get from the bottom to the top. And that's just mechanical work done, right? These problems you have, there is a worksheet for you to do. You just follow this prescription here. The network, the change in kinetic energy is not always zero. You start from, you start pushing a cart, and at the end of the motion, the cart's moving 10 meters per second. Okay. If you happen to know the normal force acting on the cart, and you happen to know the force of friction acting on the cart, you can calculate the force that you've done on the cart. You can calculate the work done by the friction on the cart, perhaps. The change in kinetic energy there would not be zero because the initial kinetic energy would be zero, but the carts have some final velocity, right? So you'd end up with 1/2 mv final squared, right? So it's actually not anything new. We could have done all this stuff by kinematics. Well, not the mountain climber, but the pushing the cart with a constant force along the ground where there's a constant frictional force, that we could have done that just using forces before, but it's so much easier just using this work energy theorem. Okay, so there is a worksheet that you will be doing. Just as a quick review here, conservation laws, when applicable, they're not always, well, conservation of total energy is always applicable, but conservation of momentum, conservation of mechanical energy is sometimes applicable. When they are applicable, it greatly aids our analysis of the physics problem at hand, okay? The work energy theorem is simply the conservation of total energy in a different form than you've used before. It can always be applied. It might not be particularly useful to apply, but when you can apply it, it's really straightforward. A little change here because we're coming up to the end. I want to give you guys enough time to get these things done. The next, the final lecture that you guys are going to have will be on Tuesday. Okay, so next time I'll put one of these up will be next Tuesday, the 19th of May. Our last lesson will be conservation of energy, conservation of total energy, which is equivalent to what we just did, but we write it differently, and conservation of mechanical energy, which is probably what you're used to from middle school. Your homework, the work energy theorem remote homework is on Classroom. That is due on Tuesday. It's not, there's 6 problems or something. They're no more complicated than what you just saw, okay? It's just keep track of the forces. President Trump jumps out of a plane. What forces are acting on him? Gravity. All right. What's the speed that he has when he hits the ground? All right. Yay. How much work is done by gravity? All right. And the second problem there is he has terminal velocity. So now there's friction. Okay. Terminal velocity means he reaches a terminal velocity. So you know his final velocity when he reaches the ground. because friction has slowed him down, and you want to find that terminal velocity. All right. So these are just identify the forces, and you will be fine. This should not take you but a half hour to get this done, truly. All right, and our last lesson will be on Tuesday, and that homework will be conservation of energy, both conservation of mechanical energy, conservation of total energy, and that homework will be due the following Tuesday also. That gives us a little bit of leeway because the end of the year is the following Friday, so it's only a couple of days there. So I hope you have enjoyed this next to last episode of our journey through physics. I hope you enjoyed my beach. And if you have any issues, contact me. And I have been sitting here next to my computer looking at Zoom all morning. Nobody has logged on. But if you have problems, email me. We'll set something up and we can get you straightened out. Okay. As always, please stay safe and enjoy your physics homework. Okay. Have a great day. Bye-bye.